What if I told you that somewhere in our night sky, right now, at this very moment, a star is dying? Not just any star, but a colossal giant so enormous that more than 400 million of our suns could fit inside it. And when this star finally dies, when it takes its last breath and explodes in the most violent event the universe has ever known, something extraordinary will happen. You will be able to see it, not through a telescope, not through some expensive equipment, but with your own naked eyes. You will step outside one ordinary night, look up at the sky you have looked at 1,000 times before, and there, hanging in the darkness like a diamond that was never there before, will be a new light. A light so bright it might rival the full moon itself. A light visible even during the daytime. A light that announces the death of a star that lived millions of years, all of its existence compressed into a single moment of catastrophic brilliance for you to witness. This is not science fiction. This is not a movie plot. This is real astronomy, real physics, and it could happen in your lifetime. It could happen this year. It could happen tonight. And when it does, it will be the first time in over 400 years that humanity has witnessed such an event with the naked eye in our own cosmic neighborhood. But here is where the story gets even more fascinating. That dying star I mentioned, that cosmic giant on the edge of oblivion, it has a name. Astronomers call it Betelgeuse. You've probably seen it without knowing what you were looking at. If you have ever gazed at the winter sky and spotted the constellation Orion, that famous hunter with his belt of 3 bright stars, then you have seen Betelgeuse. It is the reddish star that marks Orion's shoulder. That red colour, that distinctive hue that sets it apart from the white and blue stars around it, is not just beautiful. It is a warning sign. It is the colour of a star in its final stages of life, a star that has already begun its journey toward death. Now, let me share with you some facts that might make you look at the night sky very differently the next time you step outside. The last time a supernova was visible to the naked eye from Earth within our own galaxy was in the year 1604. That was over 420 years ago. That means no living human being has ever witnessed such an event. Johannes Kepler, the famous astronomer, was among those who observed that explosion, and he documented it in detail. But since then, nothing. Over 4 centuries of silence. We are, in astronomical terms, overdue for another one. And Betelgeuse is showing all the signs of a star that is preparing for its final act. Here is another fact that might blow your mind. A supernova releases more energy in a matter of seconds than our sun will produce in its entire 10 billion year lifetime. Let that sink in for a moment. Everything our sun does over billions of years, all the light and heat it provides to Earth, all the energy that powers our entire solar system, a supernova can match that in just a few seconds. The energy released is so tremendous that a single supernova can briefly outshine an entire galaxy containing 200 billion stars. One star, dying, becomes brighter than 200 billion stars combined. And here is perhaps the most profound fact of all. The atoms in your body, the iron in your blood that carries oxygen to your cells, the calcium in your bones that holds you upright, the gold in any jewelry you might be wearing, every single one of these atoms was forged in the heart of a dying star. They were created in supernovae that exploded billions of years ago, scattering their elements across the cosmos, eventually finding their way into the cloud of gas and dust that would become our solar system, our planet, and ultimately you. You're not just looking at the stars when you gaze at the night sky. You're looking at your ancestors. You're made of dead stars. So the questions that should be burning in your mind right now are these. Which star is about to explode? When exactly will it happen? What will it look like in our sky? Will it be dangerous for Earth? How do scientists know when a star is about to die? And why have we been waiting for over 400 years for this cosmic spectacle? These are the questions we're going to explore together in depth, and by the time we are done, you will never look at the night sky the same way again. Before we dive deep into this cosmic death story, I have a request for you. If you find the mysteries of the universe as fascinating as I do, if the thought of witnessing a stellar explosion excites you as much as it excites me, hit that subscribe button right now. What you're about to learn over the next hour and a half will fundamentally change how you understand the night sky and our place in the universe. This content took months of research, consulting the latest scientific studies from NASA, the Hubble Space Telescope, and observatories around the world. If you want more journeys like this through the cosmos, smash that like button. And here is something I would genuinely love to know. Drop a comment below telling me, have you ever seen anything unusual in the night sky? A bright meteor, a strange light, something you could not explain. I want to see how many future astronomers and space enthusiasts we have in this community. Now, let us begin our journey into the heart of dying stars. To truly understand what a supernova is and why we might see one soon, we first need to understand what stars actually are and how they live their lives before they die. You see, a star is not just a ball of fire floating in space, as many people imagine. A star is actually a carefully balanced cosmic dance between two opposing forces that have been locked in combat for millions or even billions of years. The first force is gravity. Gravity wants to crush the star. It pulls all the matter inward, compressing it, squeezing it tighter and tighter. If gravity had its way, it would collapse the star into an impossibly small point. But there is a second force fighting back. Deep in the core of every star, nuclear fusion is taking place. Hydrogen atoms are being smashed together under tremendous pressure and temperature, fusing into helium and releasing enormous amounts of energy in the process. This energy pushes outward, creating pressure that counteracts gravity's inward pull. For most of a star's life, these two forces are perfectly balanced. Gravity pulls in, fusion pressure pushes out, and the star exists in a state of equilibrium. Our Sun has been doing this balancing act for about 4.5 billion years, and it has enough hydrogen fuel to continue for another 5 billion years or so. But not all stars are like our Sun. Some stars are born massive, truly gigantic compared to our modest yellow dwarf. These massive stars, the ones that contain 8 times or more the mass of our Sun, live very different lives. They burn through their fuel much faster because their enormous gravity creates much higher temperatures and pressures in their cores. A star like Betelgeuse, which may have been born with 15 to 20 times the mass of our Sun, lives fast and dies young. While our Sun will shine for 10 billion years, Betelgeuse is only about 8 to 10 million years old and is already dying. In cosmic terms, that is like comparing a human lifespan to the life of a mayfly. Now, what happens when a star starts running out of hydrogen fuel in its core? This is where the story gets interesting. When the hydrogen runs low, the core begins to contract under gravity's relentless pull. As it contracts, it heats up even more. Eventually, the temperature becomes high enough that the helium ash left over from hydrogen fusion can itself begin to fuse, combining into heavier elements like carbon and oxygen. The star gets a new lease on life, but this helium fuel burns even faster than hydrogen did. For massive stars, this process continues in stages. After helium, the star begins fusing carbon. After carbon, it fuses neon, then oxygen, then silicon. Each new fuel source is heavier and burns faster than the last. The star develops layers, like an onion. With different elements being fused in shells around the core. Hydrogen burning in the outermost shell, helium beneath that, then carbon, neon, oxygen, and finally silicon in the innermost shell around the core. But here is the critical point, the moment that seals the star's fate. When silicon fusion begins, the star is producing iron in its core. And iron is the death element for stars. Every fusion reaction up until iron has released energy, which helped push against gravity. But iron is different. Iron fusion does not release energy. Instead, it absorbs energy. When a star's core fills with iron, it is like a furnace that has run out of fuel. There is no more energy pushing outward. Gravity wins. What happens next occurs in less than a second. The iron core, no longer supported by fusion pressure, collapses at nearly a quarter of the speed of light. Imagine something the size of Earth collapsing to something the size of a city in less than a second. The outer layers of the core crash inward and then bounce off the incredibly dense, rapidly forming neutron star at the center. This bounce creates a shockwave of unimaginable power. That shockwave races outward through the star, tearing it apart from the inside out. The outer layers of the star are blasted into space at tens of thousands of kilometers per second. This is a core collapse supernova, the explosive death of a massive star. During the collapse and explosion, something else remarkable happens. 99% of the energy released does not come out as light or as the expanding debris. It comes out as neutrinos, ghostly particles that barely interact with matter. Billions of neutrinos would pass through your body every second during a supernova, and you would not feel a thing because they almost never interact with ordinary matter. These neutrinos escape from the core before the light does, which gives us a unique opportunity that we will discuss later, an early warning system for supernovae. The remaining 1% of energy, the part that comes out as light and kinetic energy of the expanding debris, is still enough to outshine billions of suns. For weeks or months, a single dying star can pump out more light than all the other stars in its galaxy combined. This is the cosmic firework display we call a supernova. To put this in perspective, let me tell you about some supernovae that humans have actually witnessed throughout history. In the year 185 AD, Chinese astronomers recorded a guest star that appeared in the sky and remained visible for 8 months. They had no idea what they were seeing, but we now know they were witnessing a supernova, the explosive death of a star roughly 8,000 light-years away. This is the earliest supernova for which we have reliable historical records. Then came the supernova of 1006 AD, which was perhaps the brightest stellar event in recorded human history. Arab, Chinese, Japanese and European observers all documented this new star that appeared in the constellation Lupus. At its peak, it was bright enough to cast shadows at night, brighter than the planet Venus, bright enough to be seen during the daytime. It remained visible to the naked eye for over 2 years. Imagine stepping outside night after night for 2 years and seeing a star that was never there before, blazing with impossible brilliance. In 1054 AD, another supernova appeared, this time in the constellation Taurus. Chinese astronomers called it a guest star and recorded that it was visible in daylight for 23 days and remained visible at night for nearly 2 years. Native Americans in the southwestern United States may have recorded this event in rock art, showing a bright star near the crescent moon, which matches the astronomical conditions of that night. The remnant of this explosion is now known as the Crab Nebula, a stunning cloud of gas and energy that we can still see expanding outward today, over 900 years later, with a rapidly spinning neutron star at its center, flashing like a cosmic lighthouse. Then came 1572, when the Danish astronomer Tycho Brahe observed a new star in the constellation Cassiopeia. Tycho studied this supernova meticulously, and his observations helped overturn the ancient belief that the heavens were perfect and unchanging. The fact that a new star could appear proved that the cosmos was dynamic, that things happened in the sky. This was a revolutionary realization that helped pave the way for modern astronomy. Finally, in 1604, Johannes Kepler observed another supernova, this time in the constellation Ophiuchus. Kepler's supernova, as it is now called, was the last supernova visible to the naked eye within our own Milky Way galaxy. That was over 420 years ago. Every astronomer who has lived since then, every human being on Earth today, belongs to a generation that has never witnessed a nearby supernova with their own eyes. We are, in a sense, overdue. The Milky Way galaxy should produce a supernova roughly once every 50 years on average. Yet we have been waiting for 4 centuries. This does not mean the universe owes us a supernova, of course. Statistics do not work that way, but it does mean that a supernova in our galaxy is not a matter of if, but when. And we have identified several stars that are showing the signs of approaching death. The most famous candidate, the one that has captured the public imagination more than any other, is Betelgeuse. Let me take you on a journey to meet this cosmic giant up close. Betelgeuse sits in the constellation Orion, one of the most recognizable patterns in the night sky. Orion represents a hunter in Greek mythology, and Betelgeuse marks his right shoulder if you imagine him facing you. The star's name comes from the Arabic phrase Yad al-Jawza, meaning the hand of the central one, though centuries of transliteration have given us the name we use today. To the naked eye, Betelgeuse appears as a distinctly reddish or orange point of light, the 8th or 9th brightest star in our sky depending on when you look at it, because its brightness varies. The first thing you need to understand about Betelgeuse is its almost incomprehensible size. If you were to place Betelgeuse where our Sun sits at the center of our solar system, its outer atmosphere would extend beyond the orbit of Mars. Some estimates suggest it might even reach the orbit of Jupiter. We are talking about a single star whose diameter is roughly 1 billion kilometers. Over 700 million suns could fit inside Betelgeuse by volume, and if it were a hollow sphere, you could fit over 400 million suns within it. When we say massive, we truly mean it in a way that challenges human imagination. This enormous size is not a sign of strength, but rather a sign of decay. Betelgeuse has swelled into what astronomers call a red supergiant because it has moved into the final phases of stellar evolution. Its core is contracting and heating up, fusing heavier and heavier elements, while its outer layers have expanded outward, cooling as they go. The red color comes from this cooler surface temperature, roughly 3,000 degrees Celsius compared to our Sun's 5,500 degrees Celsius. Red stars are cooler than yellow stars like our Sun, which are cooler than blue stars. How far away is this dying giant? Distance measurements to Betelgeuse have been refined over the years, and the current best estimate places it at around 650 light-years from Earth. This means the light we see from Betelgeuse tonight actually left the star about 650 years ago, around the time of the Black Death in medieval Europe. If Betelgeuse exploded 600 years ago, we would not know yet. The information, travelling at the speed of a light, would still be on its way to us. Betelgeuse is classified as a semi-regular variable star, meaning its brightness fluctuates over time. Astronomers have identified several cycles in these variations. The primary cycle has a period of around 400 days, caused by the star physically pulsating, expanding and contracting like a beating heart. But there was also a longer secondary period of about 2,100 days, roughly 6 years, that puzzled scientists for a long time. Then, in late 2019 and early 2020, something dramatic happened. Betelgeuse began dimming more than anyone had ever seen before. Between October 2019 and February 2020, the star's brightness dropped by nearly a factor of 3. It went from being one of the brightest stars in the sky to noticeably fainter, dropping to around magnitude 1.6, the dimmest it had been in over a century of observations. The astronomical community was captivated. Media headlines screamed that Betelgeuse might be about to explode. Social media buzzed with speculation. Was this the beginning of the end? Were we about to witness a supernova? The answer, we now know, was no. But what actually happened was in many ways just as fascinating. Scientists eventually determined that the Great Dimming, as it came to be called, was caused by a massive ejection of material from the star's surface. Betelgeuse essentially sneezed, blowing off a huge amount of gas that cooled and condensed into dust as it moved away from the star. This dust cloud partially blocked our view of the star, making it appear dimmer. The Hubble Space Telescope observed the aftermath of this ejection and helped confirm this explanation. But here is what makes this even more interesting. Just recently, in January 2026, astronomers announced a groundbreaking discovery using NASA's Hubble Space Telescope and ground-based observatories. They have finally confirmed the existence of a companion star orbiting Betelgeuse. This companion, which scientists have nicknamed Betelbuddy and formerly named Suaha, has been suspected for years but never directly proven. The team, led by Andrea Dupree from the Center for Astrophysics at Harvard and Smithsonian, detected a dense wake of gas swirling through Betelgeuse's extended atmosphere, created as this companion plows through the supergiant's outer layers. Think of it like a boat moving through water, creating a ripple effect. The companion star, which orbits Betelgeuse roughly every 6 years, leaves a trail of disturbed gas in its path. This discovery helps explain some of the mysterious variations in Betelgeuse's brightness and behavior that have puzzled astronomers for decades. The companion is so close to Betelgeuse that it is actually passing through the supergiant's extended atmosphere, or is stirring up material and creating observable effects. Currently, from our point of view on Earth, Betelgeuse is eclipsing its companion star. Astronomers are eagerly planning observations for when the companion emerges from behind Betelgeuse in 2027. This will provide unprecedented opportunities to study the interaction between these two stars and better understand the complex dynamics at play. So when will Betelgeuse actually explode? This is the question everyone wants answered, and unfortunately I must give you a response that might seem frustrating. The honest answer is that we do not know precisely. When astronomers say Betelgeuse could explode soon, they mean within the next 100,000 years. In astronomical timescales, that is essentially immediate. The star is definitely in the final stages of its life, just fusing heavier elements in its core, heading toward that fateful moment when iron accumulates and gravity wins. Some recent studies suggest Betelgeuse may be in the late stages of core carbon burning, which would place it closer to the end than previously thought. but even late stages could mean thousands or tens of thousands of years. However, and this is important, it could also mean tomorrow. We simply cannot peer into the core of Betelgeuse and count how much silicon remains to be fused. We cannot know exactly when the iron core will reach critical mass and collapse. Stars do not announce their deaths on a schedule convenient for human observation. Betelgeuse could explode tonight while you sleep. It could explode while you're reading this sentence, or it could continue burning for another 50,000 years. This uncertainty is frustrating, but also thrilling. It means every night we look at Betelgeuse, we are looking at a cosmic time bomb with an unknown timer. Now let me describe what you would actually experience if Betelgeuse exploded, assuming you lived long enough to see it. First, there would be no immediate warning visible to your eyes. The light from the explosion would take about 650 years to reach us. So if Betelgeuse exploded right now in February 2026, humans in the year 2676 would be the ones to witness it. But since we do not know when Betelgeuse will explode, we do not know if the explosion has already happened. The star might have died centuries ago, and the news is still traveling toward us through the vast emptiness of space. When that light finally arrives, here is what would happen. One night, you would go outside and Betelgeuse would look normal. Maybe you would not even notice it particularly. But over the next few days, something strange would begin. Betelgeuse would start getting brighter. At first, it might just seem like the star was having one of its normal variations. But this brightening would not stop. Day after day, night after night, Betelgeuse would grow more brilliant. Within a couple of weeks, it would be the brightest star in the sky by far, outshining even Sirius. Then it would surpass Venus, then Jupiter. At its peak brightness, Betelgeuse would be visible during the daytime. You would be able to look up at the blue afternoon sky and see a star shining there, something humanity has not witnessed from a supernova in our galaxy since 1054 AD. At night, the effect would be even more dramatic. Betelgeuse would shine with a brightness comparable to the full moon, possibly even brighter. It would cast visible shadows on the ground. You could read a book by its light alone. The familiar Orion constellation would be utterly transformed, one shoulder now blazing with the intensity of a lunar disk. The color would change over time as well. Initially, the explosion would produce intense blue and ultraviolet light as the shockwave heated the outer layers of the star, but as the expanding debris cooled, the color would shift through white into yellow, orange, and eventually red. Over weeks and months, you would be able to watch this color evolution with your naked eye, like watching a cosmic sunset in slow motion. How long would this spectacle last? The supernova would remain visible to the naked eye for several months at minimum, possibly a year or more. It would gradually fade, but the transition would be slow enough that you could observe it over many weeks. Eventually, Betelgeuse would dim below naked eye visibility, but the expanding nebula of debris would remain visible through telescopes for centuries, slowly dispersing into the interstellar medium. There is one thing that would change forever, though. Orion would never look the same again. The hunter would lose his shoulder. Where Betelgeuse once shone red for thousands of years of human history, there would eventually be nothing visible to the naked eye, just the slowly expanding remnant of a star that once was. Every culture that has incorporated Orion into its mythology, every civilization that has used this constellation for navigation or storytelling, Sagittae would have to adapt to a sky that has fundamentally changed. But Betelgeuse is not the only supernova candidate that astronomers are watching closely. Let me introduce you to another star system that some scientists consider even more likely to explode in the astronomically near future, and one that might produce an even more spectacular and potentially more concerning event. This is Eta Carinae. Eta Carinae is located in the southern constellation of Carinae, which means it is best visible from the southern hemisphere. It lies about 7,500 light-years from Earth, more than 10 times farther than Betelgeuse. But what Eta Carinae lacks in proximity, it makes up for in sheer violence and instability. This is not just a star. It is a binary system containing two of the most massive stars known in our galaxy, all locked in a deadly orbital embrace. The primary star, Eta Carinae A, is estimated to have between 100 and 150 times the mass of our Sun. Its companion, Eta Carinae B, is no lightweight either, probably containing 30 to 80 solar masses. Together, this system is radiating energy at a rate 5 million times greater than our Sun. Eta Carinae has already demonstrated its explosive potential. In the 1840s, it underwent what astronomers call the Great Eruption, an event that for a time made it the second brightest star in the sky after Sirius. During this eruption, Eta Carinae expelled approximately 10 to 40 solar masses of material into space, creating the beautiful and haunting structure we now call the homunculus nebula, two lobes of gas and dust expanding outward from the central stars. Here is what makes that eruption remarkable. Eta Carinae released as much energy during the Great Eruption as a typical supernova produces. But it did not actually die. The stars are still there, still burning, still unstable. Scientists now refer to events like the Great Eruption as supernova imposters, explosions powerful enough to mimic a supernova without actually destroying the star. It is as if Eta Carinae fired a warning shot, demonstrating its destructive potential while saving its final cataclysm for later. When Eta Carinae finally does explode for real, it might not be an ordinary supernova. Because of its extreme mass, there is a possibility that Eta Carinae could become a hypernova, an explosion even more powerful than a standard supernova, potentially producing a gamma-ray burst in the process. Gamma-ray bursts are the most energetic events in the universe, focused beams of radiation that can sterilize planets across thousands of light years if they happen to be pointed in the wrong direction. Now, before you start building an underground bunker, let me reassure you about the danger assessment. First, Eta Carinae is 7,500 light-years away. At that distance, even a direct gamma-ray burst would not be immediately lethal to life on Earth. Second, and more importantly, the orientation of the Eta Carinae system does not appear to be aimed at us. The axis along which any gamma-ray burst would be directed seems to be pointed away from our solar system. While there is always some uncertainty in these measurements, the current scientific consensus is that Eta Carinae does not pose an existential threat to Earth. But it would still be an incredible spectacle. Even at 7,500 light-years, an Eta Carinae supernova would be visible to the naked eye, probably appearing as bright as Venus, or even brighter for observers in the southern hemisphere. It would be the most distant supernova ever observed with human eyes, a reminder that even across vast gulfs of space, the deaths of massive stars can still reach out and touch our skies. There are other supernova candidates worth knowing about as well. Let me briefly introduce you to some of them. Ik Pegasi is a binary star system only 150 light-years from Earth, making it the closest known supernova candidate. It consists of a main sequence star and a white dwarf. If the white dwarf accretes enough matter from its companion, it could eventually explode as a Type 1 supernova. However, this is not expected to happen for millions of years, so Ik Pegasi is more of a very long-term concern than an imminent threat. Antares, the bright red star in the constellation Scorpius, is another red supergiant similar to Betelgeuse. It lies about 550 light-years from Earth and will eventually explode as a supernova, though like Betelgeuse the timing is uncertain. Spica, the brightest star in the constellation Virgo, is also a massive star that will eventually end its life in a supernova, though it appears to be earlier in its evolutionary sequence than Betelgeuse or Antares. Then there are the Wolf-Rayet stars, evolved massive stars that have shed their outer layers and are burning helium or heavier elements in their exposed cores. CSWR-102 and WR-142 are two examples of Wolf-Rayet stars that could explode as supernovae or hypernovae in the astronomically near future. These stars are fascinating and terrifying in equal measure, naked stellar cores blazing away with surface temperatures of 100,000 degrees or more. And then there is V Sagittae, a binary system that has been making headlines recently. Located about 7,800 light-years away in the constellation Sagittae, V Sagittae consists of a white dwarf that is actively cannibalizing a companion star, stripping away its material orbit by orbit. Astronomers have been tracking this system and found that its brightness has been increasing over the past century, indicating that mass transfer onto the white dwarf is accelerating. Studies published in 2025 suggest that the Sagittae will undergo multiple powerful flare-ups before finally exploding as a nova or possibly even a supernova within the next 100 years. When it reaches its final explosive phase, it could briefly become one of the brightest objects in the sky, potentially visible during the daytime. This makes V Sagittae one of the most predictable upcoming stellar explosions, a cosmic event that people alive today might actually witness. Speaking of predictable events, I need to tell you about Eta Carinae Borealis, also known as the Blaze star. This is not a supernova candidate in the traditional sense, but rather a recurrent nova, a binary system where a white dwarf periodically undergoes thermonuclear explosions on its surface after accumulating enough material from its companion. Eta Carinae Borealis has exploded approximately every 80 years, with recorded outbursts in 1866 and 1946. Based on this pattern, astronomers have been predicting that the next outburst could happen any time now, possibly in 2026. When it goes off, Eta Carinae Borealis will briefly become visible to the naked eye, jumping from a magnitude too dim to see without telescopes to a magnitude around 2, comparable to the North Star. Astronomers have been watching this system closely, expecting it to provide a spectacular show for skywatchers around the world. The anticipation has been building, and while the star has been somewhat overdue compared to early predictions, the eruption could happen at any moment. Now that we have met the potential candidates for the next visible supernova, let us explore how scientists actually study these stars and predict their fates. How do we know when a star is approaching death? What tools do astronomers use to peer into the hearts of these distant suns? The most fundamental technique is spectroscopy, the art of spreading starlight into its component colors and analyzing the patterns that emerge. When light from a star passes through a prism or diffraction grating, it separates into a spectrum, a rainbow of colors from red through orange, yellow, green, blue, and violet. But this spectrum is not smooth and continuous. It contains dark lines, absorption lines, where specific wavelengths of light have been absorbed by elements in the star's atmosphere. Each element produces a unique pattern of these lines, like a fingerprint. By analyzing these spectral fingerprints, astronomers can determine what elements are present in a star, their temperatures, their motions, and even get hints about what might be happening deep in the stellar core. For dying stars like Betelgeuse, spectroscopy reveals the products of advanced nuclear fusion. The presence of certain elements, the ratios between them, the temperature gradients implied by different absorption lines, all of these provide clues about the star's internal state. Changes in the spectrum over time can indicate that the star is evolving, that the fusion processes are shifting, that death is approaching. Another crucial technique is photometry, the precise measurement of a star's brightness over time. As we discussed, stars like Betelgeuse pulsate, expanding and contracting, brightening and dimming. By tracking these brightness variations with extreme precision, astronomers can identify periodicities, look for anomalies, and detect events like the Great Dimming of 2019 to 2020. Modern telescopes can measure brightness changes of less than 1%, allowing scientists to detect subtle variations that would have been invisible to earlier generations of astronomers. Space-based telescopes like Hubble and the James Webb Space Telescope have revolutionized our ability to study these stars. In January 2026, Hubble observations helped confirm the existence of Betelgeuse's companion star by detecting the wake of disturbed gas it creates as it orbits through the supergiant's atmosphere. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, has been opening new windows into stellar evolution. In late 2025 and early 2026, Webb has been making remarkable discoveries, including observing supernovae in the very early universe and detecting hidden supergiant stars shrouded in dust just before they explode. These observations are teaching us new things about how massive stars end their lives. But perhaps the most exciting development in supernova prediction is the potential for neutrino early warning systems. Remember those ghostly particles I mentioned earlier, the ones that carry away 99% of a supernova's energy? Neutrinos are produced in the core collapse that triggers a supernova, and they escape from the star almost instantaneously because they barely interact with matter. Light, on the other hand, has to fight its way out through the dense stellar material, a process that can take hours. This means neutrinos from a supernova reach Earth before the light does, potentially giving us an early warning that an explosion is underway. This is where SNEWS comes in, the Supernova Early Warning System. SNEWS is a global network of neutrino detectors designed to provide rapid alerts when a burst of neutrinos consistent with a nearby supernova is detected. Facilities like Super Kamiokande in Japan, IceCube at the South Pole, and several other detectors around the world are all connected to this network. If multiple detectors simultaneously register an anomalous burst of neutrinos, SNEWS can issue an alert to the astronomical community within minutes, giving observers around the world time to point their telescopes at the sky before the light from the supernova arrives. How much warning would this actually provide? For a supernova in our galaxy, the neutrino signal would likely precede the visible light by several hours, perhaps up to half a day. This might not sound like much, but in astronomical terms, it is enormous. It would give every telescope on Earth and in orbit time to prepare. It would allow scientists to capture the very first moments of the explosion, data that has never been recorded for a nearby supernova with modern instruments. The scientific value would be incalculable. We know this neutrino detection works because it has happened once before. On February 23, 1987, 3 neutrino detectors around the world registered a burst of neutrinos about 3 hours before the light from supernova 1987A was observed in the Large Magellanic Cloud. Only about 25 neutrinos were detected in total. But this was far more than the background rate and represented the first direct detection of neutrinos from a supernova. It confirmed theoretical predictions about how core collapse supernova work and marked the beginning of neutrino astronomy. Supernova 1987. A holds a special place in the history of astronomy because it was the first supernova that could be studied with modern instruments. Located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years away, it was close enough to be observed in remarkable detail but far enough that it was not overwhelmingly bright. An astronomer named Ian Shelton was working at Las Campanas Observatory in Chile when he photographed the supernova, initially not realizing what he'd captured. When he developed the photographic plate and saw the new star, he rushed outside to confirm with his own eyes that there was indeed a bright point of light in the Large Magellanic Cloud that had not been there before. Supernova 1987. A taught astronomers many things that could only be learned from direct observation of a supernova. It confirmed that supernova produce neutron stars, as predicted by theory. It showed how the supernova brightens and fades over time, following the radioactive decay of elements produced in the explosion. It revealed the existence of rings and structures around the star that had been expelled in earlier mass loss events. The Hubble Space Telescope has been observing the aftermath of 1987A for decades, watching as the shockwave from the explosion expands outward and collides with material expelled by the star before it died. And in 2024, using the James Webb Space Telescope, astronomers finally detected direct evidence of the neutron star at the center of 1987A's expanding debris, settling a question that had remained open for nearly 4 decades. But here is the tantalizing thing. 1987A was 168,000 light-years away. Betelgeuse is only 650 light-years away. A supernova at Betelgeuse's distance would be over 200 times closer than 1987A. It would appear about 40,000 times brighter. Every instrument we have, from amateur telescopes in backyards to orbiting space observatories, would be able to study it in unprecedented detail. We would learn more about supernova physics from a single event than we have learned from all previous observations combined. It would be, without exaggeration, the astronomical event of the millennium. Now let us address the question that is probably lurking in the back of your mind. Is a nearby supernova dangerous? If Betelgeuse explodes, should we be worried about Earth? The short answer is no, we should not be worried about Betelgeuse specifically. But the longer answer involves understanding what kinds of radiation a supernova produces and how distance affects the threat. When a massive star explodes, it produces several types of harmful radiation. First, there is the electromagnetic radiation, including ultraviolet light, X-rays, and gamma rays. These can be damaging to living things and can affect a planet's atmosphere. Second, there are the particles, the cosmic rays, high-energy protons, and heavier nuclei that are accelerated by the shockwave and travel outward through space. Third, in some cases there are gamma ray bursts, narrow beams of intensely focused gamma radiation that can cause damage across enormous distances. The key factor in assessing danger is distance. Radiation from a supernova follows the inverse square law, meaning that if you double your distance from the source, the intensity drops to 1/4. If you triple the distance, the intensity becomes 1/9. By the time supernova radiation has traveled hundreds of light years, it has spread out over such an enormous volume of space that its intensity at any given point is dramatically reduced. Scientists have estimated that a supernova would need to occur within about 50 light-years of Earth to cause serious harm to our biosphere. Within this distance, the radiation could significantly damage the ozone layer, allowing increased ultraviolet radiation from the sun to reach Earth's surface. This could cause increased rates of cancer and other health effects in surface-dwelling organisms, kill off plankton in the upper ocean, and potentially trigger mass extinctions if severe enough. Some scientists have proposed that past mass extinctions might have been caused by nearby supernovae. The late Ordovician extinction, which occurred about 445 million years ago and killed roughly 60% of marine genera, has been hypothetically linked to a gamma-ray burst or supernova. The timing and pattern of extinctions could be consistent with a sudden burst of radiation damaging the ozone layer. However, this remains speculative, and there is no direct evidence confirming that a supernova caused this particular extinction. Now, how does Betelgeuse measure up against this danger threshold? Betelgeuse is approximately 650 light-years away. That is more than 10 times the estimated danger zone. At this distance, the radiation from a Betelgeuse supernova would be reduced by a factor of over 100 compared to a supernova at 50 light-years. We would receive a burst of neutrinos that would pass harmlessly through Earth. We would receive an increase in cosmic rays over the following years as the fastest particles reached us, but this increase would be modest and not dangerous. We would receive some X-rays and gamma rays, but the atmosphere would absorb most of these, and the total dose would be negligible. In short, a Betelgeuse supernova would be a spectacular show with no harmful effects on Earth. What about Eta Carinae and the gamma-ray burst concern? This is where things get slightly more complicated. As I mentioned, Eta Carinae might produce a hypernova with an associated gamma-ray burst when it finally explodes. Gamma-ray bursts are dangerous because they are focused, like a cosmic laser beam. The energy that would normally spread out in all directions is instead concentrated into a narrow jet. If that jet happens to be pointed directly at your planet, you receive a massive dose of radiation even from enormous distances. However, current observations suggest that Eta Carinae's rotational axis, which would define the direction of any gamma-ray burst, is not pointed at Earth. The jets would fire off perpendicular to our line of sight, sparing us from the most dangerous component of the explosion. Furthermore, Eta Carinae is 7,500 light-years away, well outside even the extended danger zone for gamma-ray bursts, which is typically estimated at a few thousand light-years for direct hits. The scientific consensus is that neither Betelgeuse nor Eta Carinae poses a significant threat to life on Earth. We can look forward to their eventual explosions not with fear, but with eager anticipation. They would be gifts from the cosmos, opportunities to witness and study the most powerful events in the universe from a safe and advantageous vantage point. Let me now take you into the aftermath of a supernova. What happens after the explosion fades from view? What does a dead star leave behind? The immediate aftermath of a core collapse supernova is a rapidly expanding shell of debris, gas, and dust enriched with heavy elements forged in the explosion. This material expands outward at speeds of thousands of kilometers per second, glowing as it cools, forming what we call a supernova remnant. Over centuries and millennia, this remnant continues to expand, sweeping up interstellar material, creating shock fronts that glow in radio waves, X-rays, and visible light. We can see supernova remnants from past explosions all across the sky. The Crab Nebula, remnant of the 1054 supernova, is perhaps the most famous. It is a roughly 10 light-year wide cloud of filamentary gas, still expanding, still powered by the central pulsar that spins 30 times per second and shoots out beams of radiation like a lighthouse. The Veil Nebula in Cygnus is the remnant of a supernova that exploded between 10,000 and 20,000 years ago, its delicate wisps of gas stretching across a region larger than the full moon. Cassiopeia A, though invisible to the naked eye, is one of the youngest supernova remnants in our galaxy. The debris from a star that exploded around 1680 AD, though the light may have been obscured by dust. At the center of many supernova remnants lies one of the most extreme objects in the universe, a neutron star. When the core of a massive star collapses, protons and electrons are crushed together to form neutrons. The result is a sphere of neutrons only about 20 kilometers across, but containing 1 to 2 times the mass of our Sun. The density is beyond comprehension. A teaspoon of neutron star material would weigh about 1 billion tons, more than Mount Everest. Neutron stars also have the strongest magnetic fields in the universe, trillions of times stronger than Earth's magnetic field. As they rotate, these magnetic fields sweep around like the beam of a lighthouse. If the beam happens to point toward Earth during part of the neutron star's rotation, we see regular pulses of radio waves, X-rays or gamma rays. We call these objects pulsars, and they are among the most precise clocks in the universe, rivaling the best atomic clocks we can build. Some neutron stars have even more extreme magnetic fields, 1,000 times stronger than typical pulsars. These are called magnetars, and they occasionally experience starquakes when their solid crusts crack and release enormous amounts of energy. A magnetar flare in 2004 from SG R1806-20, located about 50,000 light-years away, released more energy in 1/10 of a second than our Sun produces in 100,000 years. Even at that enormous distance, the radiation measurably affected Earth's ionosphere. If the core of the collapsing star is massive enough, above about 3 solar masses, even neutron pressure cannot halt the collapse. The core continues contracting until it crosses a threshold from which nothing can escape, not even light. It becomes a black hole. Stellar mass black holes born in supernovae typically have masses between 3 and 20 times that of our Sun. They are invisible except for their effects on surrounding matter. If gas falls toward a black hole, it heats up to tremendous temperatures as it spirals inward, emitting X-rays that we can detect. Several dozen stellar mass black holes have been identified in our galaxy through these emissions. But the supernova leaves behind more than just compact objects. It spreads the elements forged in the explosion across space. During the explosion, the extreme conditions allow nuclear reactions that cannot occur during normal stellar burning. Elements heavier than iron, including copper, zinc, silver, gold, platinum and uranium, are created in the supernova fireball through a process called rapid neutron capture, or the R process. Without supernova, these elements would not exist in significant quantities anywhere in the universe. This brings us back to one of the most profound realizations in all of astronomy. You're made of supernova debris. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these were forged in the nuclear furnaces of ancient stars and scattered across space when those stars exploded. We are quite literally the children of dead stars. Carl Sagan famously said that we are star stuff, and he was speaking a literal truth. Every atom of your body more massive than hydrogen and helium has a story that includes the death of a star. But the connection goes even deeper. Supernova explosions do not just spread elements, they can trigger the formation of new stars and planets. When the shockwave from a supernova encounters a cloud of interstellar gas, it compresses that cloud, potentially pushing it over the threshold needed for gravitational collapse. The supernova seeds the cloud with heavy elements while simultaneously providing the nudge needed to start the collapse. Some scientists believe that our own solar system was formed this way, that a nearby supernova about 5 billion years ago both triggered the collapse of the gas cloud that became our Sun and provided the elements that would eventually form the rocky planets, including Earth. So supernovae are not just spectacular deaths, they are cosmic engines of creation. In their destruction, they sow the seeds of new stars, new planets, and potentially new life. The universe recycles its matter through generations of stars, each cycle enriching the cosmos with heavier elements, building complexity from simplicity. We are part of that cycle. When you look at a supernova, you're looking at both an ending and a beginning. Let me now take you through the human experience of witnessing a supernova, both in history and in the hypothetical future. What would it mean for our species to see such an event? Throughout human history, supernovae have left their mark on culture and consciousness. Ancient peoples did not understand what they were seeing when a new star appeared in the sky, but they understood that something momentous was happening. Chinese astronomers kept meticulous records of guest stars, noting their positions, brightness, and duration. These records have proven invaluable to modern astronomers trying to identify which supernova remnants correspond to which historical observations. The supernova of 1054 AD may have had cultural impacts beyond mere record-keeping. Some researchers believe that the famous star depicted in Anasazi rock art in Chaco Canyon, New Mexico, represents the supernova of 1054. The rock art shows a crescent moon next to a bright star, and astronomical calculations confirm that the moon was in its crescent phase and positioned near the supernova in July 1054. Whether this interpretation is correct remains debated, but it suggests that the event was noticed and commemorated by people across the world. The supernovae of 1572 and 1604 had profound impacts on European astronomy and philosophy. When Tycho Brahe observed the new star of 1572, he carefully measured its position night after night and found that it did not move relative to the background stars. This proved it was not a nearby phenomenon like a comet, but something in the realm of the fixed stars, which Aristotelian philosophy held to be perfect and unchanging. The appearance of a new star challenged the entire worldview. Similarly, Kepler's supernova of 1604 provided fuel for the scientific revolution that was then underway, evidence that the heavens were not static but dynamic. What would happen if a supernova visible to the naked eye occurred today? The cultural impact would be enormous, though different in character from historical events. We live in an age of instant global communication. Within minutes of the first observation, news would spread around the world. Social media would explode with photos, speculation, and excitement. Amateur astronomers would rush outside with their telescopes. Professional observatories would drop whatever they were doing and begin intensive observation campaigns. For the scientific community, it would be the event of a lifetime. Every telescope capable of observing the supernova would be pressed into service. Satellites would be redirected. Data would flow in quantities never before seen for any astronomical object. The supernova would be studied across the entire electromagnetic spectrum, from radio waves to gamma rays. We would finally have the detailed observations needed to test our theories of supernova explosions in ways that distant supernovae cannot provide. But beyond the science, there would be a deeper human experience. For perhaps the first time in over 4 centuries, people around the world would look up and see something new in the sky, something that was not there before, something that signals the death of a star and the creation of new elements. It would be a shared experience across all of humanity, a moment when we would all be looking at the same cosmic event, reminded of our smallness and our connection to the vast universe around us. Some people would find it terrifying. Despite reassurances from scientists about the lack of danger, the sight of a new star might trigger fears about the end of the world or divine judgment. Throughout history, unusual celestial events have been interpreted as omens, and supernovae are no exception. Media coverage would need to carefully balance the excitement of the discovery with clear communication about the absence of any threat to Earth. But I think more people would find it inspiring to see with your own eyes an event of such cosmic magnitude, to know that you are watching a star die and spread its elements across space, to understand that you are part of the same cosmic story. That can only be described as a spiritual experience, regardless of one's religious beliefs. It would be a moment of collective awe, a reminder that the universe is far stranger and more beautiful than our daily lives usually allow us to appreciate. Let me now turn to how we are preparing for the next nearby supernova, and what you can do to be ready to witness it when it finally happens. Professional astronomers have been preparing for decades. The SNEWS network I mentioned earlier is operational and ready to send alerts when neutrinos from a galactic supernova are detected. Protocols are in place at major observatories for responding quickly to such alerts. Software pipelines have been developed to rapidly process and analyze the flood of data that would come from a nearby supernova. Theorists have run countless simulations of supernova explosions, making predictions that can be tested when we finally get to observe one up close. But you do not need to be a professional astronomer to enjoy a supernova. If one occurs, here is what you should do. First, simply go outside and look up. For a supernova like Betelgeuse, no equipment would be necessary to see it. In fact, binoculars or telescopes might show you less than your naked eye because the light would be so intense. Just find a spot with a clear view of the relevant part of the sky and look. If you want to document your experience, a simple camera or smartphone can capture the supernova. Nothing fancy is required. The supernova would be bright enough to photograph with any camera capable of capturing stars. Over successive nights, you could document the changes in brightness and color, creating your own record of this historic event. If you are an amateur astronomer with a telescope, there are more detailed observations you could make. Measuring the supernova's brightness precisely using standard photometric techniques would contribute valuable data. Attempting spectroscopy, even with simple equipment, could reveal information about the chemical composition of the expanding debris. Many amateur astronomers have contributed to supernova science over the years, and a nearby supernova would provide unprecedented opportunities. Most importantly, take the time to simply experience it. Do not spend the entire event looking at screens or checking social media. Sit outside under the stars, contemplate what you're seeing. A star that burned for millions of years is dying before your eyes. Elements that will become part of future stars, future planets, maybe future living things, are being scattered across space. You're witnessing one of the great cycles of the universe, the process by which complexity emerges from simplicity, by which dead stars give rise to new worlds. While we wait for a supernova that may or may not happen in our lifetimes, there are other celestial events you can observe that give some sense of the cosmos's dynamism. The recurring nova Coronae Borealis, if it erupts as expected, would be visible to the naked eye. Meteor showers occur regularly throughout the year, offering chances to see debris from comets and asteroids burning up in our atmosphere. Eclipses, both solar and lunar, as demonstrate the clockwork precision of celestial mechanics. Bright planets like Venus, Jupiter, and Mars put on shows that rival the brightest stars. The Milky Way itself, visible from dark locations, is the combined light of hundreds of billions of stars, each with its own story. Now, as we approach the conclusion of our journey together, let me reflect on what it all means. Why do we care about supernovae? Why should the death of a star hundreds of light years away matter to any of us? I think it matters because understanding supernovae is part of understanding ourselves. We cannot make sense of our own existence without grappling with the processes that made us possible. The atoms in your body were forged in stars and scattered by supernovae. The solar system you live in may have been triggered to form by a supernova shockwave. The heavy elements that make technology possible, that make biology possible, exist only because of stellar explosions. We are children of the stars in the most literal sense. It matters because supernovae connect us to the large-scale story of the universe. When we study supernovae, we are studying the processes that drive cosmic evolution. We are learning how galaxies change over time, how the chemical composition of the universe has evolved, how the conditions for life have gradually emerged across billions of years. Supernovae are not just pretty explosions. They are key players in the cosmic narrative. It matters because confronting the death of a star puts our own mortality in perspective. We worry about the length of our lives, about the eventual death of everyone we love, about our own ending. But here is a star that lived millions of years and is now dying in an instant of cosmic fire. Here is an event that makes human timescales seem almost infinitesimal, yet that star's death is not meaningless. It creates the conditions for new things to exist. Its end is also a beginning. Perhaps there is a lesson there for us, or at least a comfort. And it matters because witnessing a supernova would be one of those rare experiences that unifies humanity. In our fractured world, where we are divided by nations, religions, ideologies, and all manner of human conflicts, the sight of a new star in the sky would be shared by everyone who bothered to look up. It would remind us that we all live on the same small planet, orbiting the same modest star in the same vast universe. We're all in this together, all made of the same stellar debris, all looking up at the same sky. The supernova that will be visible from Earth is out there somewhere. It might be Betelgeuse on the edge of collapse, its core fusing the last of its silicon into iron. It might be Eta Carinae, that monstrous binary system radiating the energy of 5 million suns. It might be Sagittae, the cannibal star system that astronomers predict will explode within the century. It might be a star we have not even identified yet as a candidate, a massive star hiding in the dusty reaches of our galaxy, preparing for its final act without our knowledge. Whenever it happens, whether tonight or 1,000 years from now, that supernova will be a gift. It will be a chance to witness the grandeur of the cosmos, to see with our own eyes the processes that made our existence possible. It will be a moment of connection with the universe and with each other. It will be a reminder that we are small, but we are part of something unimaginably vast and beautiful. So tonight, if you have a clear sky, go outside and look up at Orion. Find that reddish star marking the hunter's shoulder. That is Betelgeuse, a cosmic giant nearing the end of its journey. It has been burning for millions of years, longer than our species has existed, longer than any civilization has flourished, and yet, in cosmic terms, it is almost over. Betelgeuse is in the final chapter of its story. Watch it. Remember that the light you're seeing left that star about 650 years ago, when medieval knights still rode across Europe and the Renaissance was yet to begin. By now, Betelgeuse may have already exploded. The shockwave may be tearing through its outer layers at this very moment, and we would have no way of knowing. The news, travelling at the speed of light, might still be centuries away, or perhaps the explosion will happen next year, 100 years from now, or 50,000 years from now. We cannot know. We can only watch and wait and wonder. And in that watching and waiting, we participate in one of the oldest human activities, looking up at the stars and trying to understand our place in the universe. The universe is vast beyond comprehension, ancient beyond reckoning, and indifferent to human concerns. And yet, here we are, thinking about it, studying it, telling stories about it. We are the universe become aware of itself, made of star stuff that has developed the ability to contemplate its own origins. Every supernova that has ever exploded is part of our ancestry. Every supernova yet to come will continue the story. When the next one visible from Earth finally occurs, whether in my lifetime or in the lifetime of generations yet unborn, I hope that whoever witnesses it will feel what I feel when I contemplate these cosmic events. A sense of awe at the scale and beauty of the universe. A sense of connection to the processes that made us. A sense of humility at our smallness, balanced by a sense of wonder at our ability to understand so much. And a sense of gratitude for the opportunity to be here, to look up and to see. The supernova is coming. It has always been coming, since the first massive stars formed billions of years ago. Stellar death is not a tragedy in the cosmic scheme of things. It is how the universe renews itself, how it builds complexity, how it makes planets and oceans and mountains and trees and people. The same processes that will one day end Betelgeuse have already made everything we know and love possible. So do not fear the supernova. Anticipate it. Hope for it even, if you share my desire to witness one of nature's grandest spectacles. And in the meantime, go outside and look up. The night sky is putting on a show every single night, even if it lacks the drama of an exploding star. The stars are there, the planets are there, the Milky Way stretches across the darkness. It is all waiting for you. We are made of stars. When a supernova finally blazes in our sky, we will be looking at our family, our origin, our destiny. We will be looking at ourselves. Go out, look up, wonder. The universe is calling. And now you know what to look for when it finally happens. The reddish shoulder of Orion waiting to blaze brighter than it ever has before. The Southern Cross, watching over Eta Carinae as it prepares for its final act. The Coronae Borealis, where T. Coronae Borealis awaits its next eruption. The Sagittae, where V. Sagittae is devouring its companion star, building toward an inevitable explosion. The next chapter of cosmic history is being written above our heads, in nuclear fire and starlight, in the slow fusion of elements and the sudden collapse of cores. We are privileged to live in an age when we understand what we're seeing, when we can appreciate the science behind the spectacle. Our ancestors looked at guest stars and wondered if the gods were angry. We look at supernova candidates and wonder about the physics of stellar collapse. The formation of neutron stars, the synthesis of heavy elements. But in our understanding, we have not lost the wonder. If anything, knowing what supernovae are makes them more awe-inspiring, not less. A supernova is not just a bright light in the sky. It is a neutron star being born. It is gold and silver and uranium being forged. It is a shock wave that will compress gas clouds and trigger new star formation. It is a contribution to the ongoing story of cosmic evolution that stretches back billions of years and will continue for billions more. The supernova that will be visible from Earth is not just a future event. It is part of a timeless process. Stars have been dying in spectacular explosions since there were stars to die. Every atom of iron in your blood was once in the heart of a star that exploded long before our sun was born. You carry the legacy of supernovae in your very cells. The supernova yet to come is just the latest in a chain that stretches back to the earliest generations of stars in the universe. When it finally happens, When Betelgeuse or Eta Carinae or some unexpected candidate lights up our sky, remember this. You're watching the process that made you. You're seeing the creative destruction that built the elements, the planets, and ultimately life itself. The star that dies gave something to the universe that will last forever, contributed to the cosmic pool of elements that future stars and worlds will draw upon. In that light, there is meaning. In that explosion, there is creation. In that death, there is life, and you are part of it all. This is the story of the supernova that will be visible from Earth. A story of dying giants and newborn neutron stars. A story of elements forged in nuclear fire and scattered across the cosmos. A story of human observers watching the sky across thousands of years, recording guest stars and wondering at their meaning. A story that connects the larger scales of the universe to the atoms in your body. It is your story. It is all of our stories, and it is still being written, one stellar heartbeat at a time. Look up tonight. Betelgeuse is there, waiting. And so are you. The next supernova is out there. It is just a matter of time. Until then, keep watching the stars, keep wondering about the universe, keep asking questions. That is what makes us human. This drive to understand, to reach beyond ourselves, to connect with something larger than our individual lives. The cosmos is vast, but we're not insignificant. We are made of the same stuff as the stars. We are the universe contemplating itself, and when the next supernova blazes forth in our sky, we will be there to witness it, to study it, to be changed by it. That is the greatest gift the universe can give us. The chance to understand, even if only a little. The chance to witness, even if only briefly. The chance to be part of the story. The supernova will come, the sky will blaze, and humanity will look up together and wonder. That is what we do. That is who we are. Star stuff looking at stars, waiting for the next explosion, ready to be amazed. The universe has not disappointed us yet, and it never will. End